start recording this. We'll share my screen. And today we'll finish up talking in the later chapters. I keep to the lower chapters, but I jumped out for 27, 28, and 29 just because of the added benefits of information that they had. So we did 27 and 29, and now we'll talk about chapter 28 today, which is overcurrent protection. So fuses, basically it's fuses and circuit breakers, right? The types that we use and expect to see out there, even some of the old styles. What do you do when you run into an old style and have to deal with it? And again, things are grandfather claused in to a certain point. But so, as you guys have found out from doing the homework and everything, but what do they mean by overcurrent protection? So if you looked up in this NEC Article 240, it pretty much states that for residential services, branch circuits and feeders, this protection is provided by circuit breakers or fuses. Meaning that if any given line were to experience an extreme current draw of some sort, that something on that line supplying that voltage is going to disengage and keep the power from feeding it. And this is for fire prevention and things like that, other dangers that could be happening. So the very basic ones that they first came up with were fuses in different styles, but generally it's like a metal filament, and it'll have a certain width and to it, and that's basically designed to handle the currents up to what it's rated for, and then anything over and above that for a given time period would eventually burn through that filament and disengage. Anyway, so fuses and circuit breakers are sized by matching the amp ratings to your conductor ampacities and connected load currents. So when you go through and like say you were doing your lights and you did a given section of lighting on a branch circuit, and you have a 15 amp disconnect to it, a 15 amp breaker, circuit breaker, if you will, or a 15 amp fuse. But generally then your wiring and everything else would be sized to handle with 120 volts, right, of up to 15 amps for that line. Anything over and above that 15 amps, and this device would disengage and kill the power feed to that line. So here we see an illustration. Essentially, here's a coil, if you will, of 240 volt source feeding into a given circuit, and on both sides of that are what they have 15 amp fuses rated here. You can see that these are intended to disengage if the current exceeds this rating. We basically apply a basic Ohm's law, right? I is equal to E over R, and with the ratings that we have available to us here, we have A, we have the voltage source, B, we have how much resistance we're going to experience here. So we can quickly go through boom, 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 and calculate how much normally will this pull. And so you can see it doesn't even quite hit 10 amps with the amount of load resistance on this given line. So this would be a normally operating circuit. Current's flowing through nicely. We're not going over what the fuse is rated for or anything like that. Now we look at something where, yes, we have the overloaded circuit. Very similar circuit, except now our resistance has gone up. In this case, we experienced, let's say, a short circuit that ended up throwing us 24 ohms into a parallel configuration, if you will. And what ends up happening is the resistance, basically, as you can see, it goes down to 12 ohms. Now, Ohm's law is very directly relational. So in this case, If we still, things remaining the same, right? The voltage hasn't changed at all, so it's still 240 volts. But now our overall resistance is down in the 12 ohms range, and you can see that now we're ended up pulling nearly 20 amperes, and 20 amperes will exceed the rating of that fuse. So for whatever reason, device malfunction, you ended up getting a short circuit involved or something like that, and you end up pulling a lot more current than what you're expected to. Then what's going to happen is these fuses are going to give way and pop, and basically disengage the voltage feeding that line. So what do we experience when we get a short circuit? Well, a short circuit would be a hard short where pretty much somewhere along the line the wiring has become crossed together. Maybe insulation was bare or stripped or something like that. What ends up happening is it's bypassing this device altogether. And the way current works is it'll follow the path of least resistance. So it'll flow, but it likes to flow to the easy spots. He's lazy. He wants to go wherever it's the easiest way, and it will. So if you give it an opportunity, so in this case, let's say we somehow have a wiring short like this, bypassing is 24 ohms altogether, as you can see here, then we end up coming out with pretty much 0 ohms, and following through in the Ohm's law calculation here, you can see that, hey, we're getting really low amperage. So what happens? Fuses won't pop. Your stuff is not working now. But the conductors can get really hot. And a weird situation, and let's say, and being nylon, if they get hot for a given amount of time, the insulation can melt off. And when it does, you end up getting wires crossed and this and that. This is, I don't want to say it's like a common occurrence, but this does happen. And there's different reasons why. I mean, we could go back and analyze what happened. Maybe the staple that they were using to apply the Romex or something like that was pounded in too much and was putting too much stress on the wire. And then over time with heat and whatnot, it ended up becoming disengaged or something like that. There's so many different scenarios we could follow through and see why does the insulation come away. There's so many different causes, but then the result is the same. So our current stays really low, but what ends up happening is we get no work output. I mean, basically whatever we have on this end designing, to be working under this amount of current is not happening. So if this is like, say, a light branch or something like that, you go to turn this thing on and nothing is happening at all. But your circuit breaker doesn't trip, so you're not pulling too much current. This is probably one of the more complicated, complex type of scenarios that you would run into out there trying to figure out what exactly happened. And it does happen, and a lot of times what you'll end up doing, unfortunately, is repulling the wire into that, because now your wiring's been compromised. And this happens in a lot of, instances, storefronts, homes, industrial settings. For whatever reason, something happened, something occurred, and we ended up coming up with a short circuit. Not a fun one. Then we get what they call a ground fault. So what do they mean by that? And so the definition, it says condition when a hot or ungrounded conductor, in this case our black line here, comes in contact with a grounded surface. So what this is illustrating is this is a pipe like EMT, so it's metallic. So you had a break in the insulation, and what ends up happening is the pipe will be grounded, and so when this thing makes contact with that pipe, it basically creates a ground fault, if you will. And generally that type of thing, it depends. It can happen in a few different ways, but anyway. And then we look at something called the open circuit. Now the open circuit, simply there's nothing happening here. You're literally getting 0 amps, and this is a dead giveaway for you. If you have to troubleshoot a situation like this, you go out to where your device is located or whatever, and you go and read across it. You have literally 0 amps. You go back here, you see your voltages there, your voltage is there. It's like, okay, what's happening here? Well, by basically just basic troubleshooting, you'd be able to find out very quickly that you have a break in your line somehow. And again, what is this going to involve? It's going to involve probably you pulling in some more wiring. For whatever reason, something might have happened. Who knows? There's so many different situations. It's not even funny. A mouse got into your crawl space or something and chewed the way through the insulation. And you wouldn't think, but this does happen. I had a situation with my condenser unit for my AC outside, and the one this is a couple years ago, and spring had come and we were gonna fire up the AC the first time and it wouldn't come on. So I go out in the garage, I go up, the circuit breaker's tripped, I go and flick it and it immediately trips again, and I'm like, oh great. So I go out back to the unit, I open up the disconnect box and the fuses are okay. So I was like, oh, okay. So I ended up opening up the wiring enclosure on the condenser unit itself, and the mice had literally built a nest with like moss and all kinds of weird little forest things, I guess, and had ended up stripping away the insulation on my wires inside really badly. Surprisingly, there were no dead mice in there, but but yeah, I was making a hard short. I ended up having to basically repull the line all the way through the seal tight back to the little disconnect box right there. And after that, my AC worked fine. But yeah, mice and Romex are not very good things. That's why in a lot of ways, running through like EMT through a house, it at least protects your wiring from things like that. But in any case, but yeah, this situation can occur. There's different things that can happen that'll involve. It's not always critter related. Who knows? Something happened. A ladder fell in the garage and hit a line, something goofy, but there's so many different scenarios, but you end up getting it open, and that's a pretty dead giveaway. No current whatsoever. You do have voltage at the source, then yeah, you get an open, broken line in there. So those are pretty much like your main scenarios that you'll ever run into, right? The overload where the device is shorted out, the short circuit where a wiring has shorted out, the ground fault where somehow, somewhere you got your hot is being tripped out to ground. And this doesn't have to happen in a pipe. It can also happen in the junction boxes or something like that. Who knows? There's so many different reasons. And finally, the open circuit. And the next thing that the chapter talks about is fuses. Now, these are plug fuses. They were very common when I was growing up. Actually, like half the places seem to have these, and the other half were doing a new style with the circuit breakers. Now, these styles, they had pretty much from 0 up to 30 amps, and pretty much the three you see listed here are the three most popular styles they had. In fact, when I was renting apartments, really the only two, you always had like a couple of boxes of each of these sitting on the damned on the service panel of your house, because if one popped in the middle of the night or something, there's no hardware store open, so you'd always have like a box of 15s and a box of 20s sitting there just in case. But yeah, they were colored like this just to show you the difference, but also the screw size, the bore size, how round it is, was different for each one. So you couldn't just mix and match and by accident screw the wrong one in. But yeah, they were all different size, so each type holder would only accept that kind of fuse. So what they ended up doing, this was always a fun one. Anyway, I'll get back to that. But So all new plug fuse installations shall be type S fuses, according to Article 240.52. Why? And going through the homework, you should have found that, at least from the ones that I was able to read through. All Edison-based fuses are interchangeable, NEF from 0 to 20. So how do they rate it? Well, we got three styles from 0 to 15, 16 to 20, and 21 to 30. And these are three sizes that are not mix and match, if you will. But so yeah, you could limit it down. You could buy specialized fuses back then that would limit you to like a 5 amp or something like that. But the 15, 20, and the 30 were the pretty most popular size ones. And then what they came up with was, you wouldn't think they would have allowed this, but these adapters. So they could fit in. So let's say, I don't know, you're tripping a fuse a lot, so your 15 kept popping because you had so many things plugged into it. Remember, a lot of these were 60 amp services back then. So, you know, as you started getting into the more modern age, and we have, of course, what we have more of than they had back then is more toys, right? We have a lot more appliances, and the appliances we do have are drawing a lot more power than they used to. But so what they would do is they would have these adapters. You could screw it in, and then instead of a 15, now you could have a 20 amp. Now remember, you haven't changed your wiring size. You know, again, who's the most dangerous one out there, right? Homeowners and renters. But because you have just enough knowledge to go, oh yeah, we could change that up. But by not changing your wiring size, right, if you kept running this thing or something like that, what's going to end up happening is your wiring is going to end up getting hot. You know, if you were using like number 14, which can typically handle 15 amps of current, now you're starting to pull over that on it. Yeah, you're going to start running hot on some of those lines, which could be a no-no. But but this style has been phasing out over the last, I don't know, 30 years, I guess. It's going more to the electromechanical circuit breakers. Easier. You don't have to, you know, go out and buy a box of fuses and whatnot. You just basically turn your breaker back on, unless the breaker went at fault, which rarely happens, but it can. And as long as everybody's going through and once a month and testing all their breakers out, you know, they'll work properly, right? Yeah. But yeah, and I know nobody does that, but I mean, if we did a show of hands, I have two people. But if we did do a show of hands amongst, you know, an average person, it's like how many people can actually say they've gone through on a monthly basis and tested all their circuit breakers off in their home. It's like, yeah, you usually don't get too many hands going up in the air. And I do. It's silly, but it's a good practice. That way, you know, your circuit breakers are working or not working. So, but another type they have, and this one's still very widely used out there. A lot of devices use them. You can still use them in a home. I know, you know, I'll brag like my disconnect for my condenser unit. I have two bus fuses in there, you know, big guys. But and they have and there's different types, okay, as far as their time characteristics, because it's all a matter of how quick you want the fuse to blow, okay? So the thing to think about is when you first turn something on is what does current do? So the very first thing that's going to happen, and this doesn't matter what it is, okay? The minute you first turn the device on, it's going to get an instantaneous rate of charge, okay? So it's going to pull current in, and it's actually going to draw more current than it normally uses, and that's to energize all the devices it has and things like that. So when you first turn a device on, if we were to monitor like the current draw of it, and let's say, I don't know, the device normally pulls 10 amps of current, which would be a lot, but let's say it draws 10 amps of current. Now, if we were to monitor it when we first turned it on, we would notice that it drew 12 amps of current, let's say, but it settled down fairly quickly in a very small amount of time. Now, it's when the device doesn't settle down that we have a problem, like for the device is malfunctioning in some which way, okay, drawing too much current, now it's going to become a danger. Well, the way these fuses are set up is by a time delay. So this way, you don't want the time delay to be so short that it's always going to trip every time something powers up, because it's always going to have that instantaneous rate of charge and then settle down. So you want to give it that time. And then, of course, if it hasn't settled down within the allotted amount of time, then for protection, you want your circuit breaker to trip, protecting you and protecting the device, from bursting into flames or exploding or God knows what. But so these types are all set up for different time bases, and it depends on the device. They even have like these the cartridge style ones. They even have ones they call slow blows, which now take an extraordinarily long amount of time. But let's say for whatever reason that you're using it for, you want that additional time. Maybe this device takes longer to charge up and settle down properly or something like that, in which case, yeah, you would want this slow blow on there that's still going to protect it, but at the same time, not blow out every single time that this device has gone over what it's normally rated for. So yeah, so they have the different styles, and these styles like this, there's a melt away kinds. Basically it would char. You would notice it's like all blackened and everything. It's what's inside of yours, like some kind of a filament. Um, there's even the glass styles where they have like a spring coil wrapped around a rod of ceramic, and these all, and they're all with the same purpose in mind. Okay, they're all for protection. They're all meant to blow over a given amount of current, and really what it comes down to is the time base involved. So don't just think that you mix and match them and you put a different one in, and if it's rated for 20 and the other one was rated for 20, that this is an okay thing. You want to make sure it's the same exact style, because they do have the different ones, and it will be a different time base involved, and that's really what you're looking at. Now, circuit breakers, a little different, but the good thing about circuit breakers is your initial cost is right at the installation. After that, they're pretty much reliable through the life of the home. Don't want to say forever, because nothing's forever, but circuit breakers have a good life to them. But if we were to look through and if we looked at, we just see that Article 240 is where this deals with circuit breakers, specifically in Section 80 and Section 86. Will give you the requirements for circuit breakers, and this will show you like, okay, what is it meant to do, what style does it have to be, that kind of thing. So they're old school. It's a mechanical, it's a thermomagnetic circuit breaker. So basically, as the current rises, the spring tension becomes greater and greater until finally, if it reaches, let's say if it's a 20 amp and it reaches 25 over a given amount of time, what it'll do is it'll start to flex, and then it stays on over that time, and it goes boop. And again, it's all time rating. I mean, they could make it a shorter time, but again, you would have to be turning your circuit breaker on every time you turn the vacuum cleaner on or something like that. So this is why it always takes it a second. It seems like, oh, it's going to take a second before it trips, and it's like, yeah, it will. But the NEC will permit 100% loading on an overcurrent device only if it is listed for that. And what do they mean by that? Well, that typically in a house, we don't usually load a line up 100%. Typically, your best practice is about 80% load, because you never really want to quite hit that threshold. So let's say you have a 20 amp line within your house, okay, and you have enough devices on, I don't know, a workshop or something like that, that you're constantly pulling near the 20 amp margin, like on a very regular basis. Yeah, if you keep hitting that 20, and remember, this is never going to be a dead line. It's always going to fluctuate. So depending on what you're doing, it might over a certain amount of time, it would trip. So if you were planning on having something like that, you would have to literally go out and buy a specific circuit breaker designed to handle that loading factor, that it's going to be okay. So now and it's going to be a little pricier, of course, right? You're given your standard style, because it's going to be more sensitive as far as the little electromagnetic coil it has inside. Yeah, but typically what we plan for is an 80% factor. That's usually very standard for going into a house. So unless you're actually planning for a specific area to go through with this 100% loading, this is your best line right here, is 80%. There's another area where we don't follow that rule, but we'll get into that in a little bit. So pretty much you got to think about what you got going in your house. Okay, I got two different 120 lines coming in and a neutral. Okay, neutral, of course, is not going to get a circuit breaker of any kind. So very typically, the most populous tile breakers I'm going to have in my panel are going to be single pole breakers, meaning one line. Okay, single pole, 120 volts. Now, in the areas where I got my workhorses, right, where I'm going to have motors and things like that involved, so I'm going to have a 240 volt line involved in that. Well, that's known as a two-pole breakers, which means I'm going to have both hots on this thing, two hots going on to it. And you can see, even if we compare, the one on the right is a single pole breaker meant for one line coming in, compared to this big boy on the left, and he's meant to handle two lines going into him. So you can even see by the shaping of it that they even look different. So you can very, very typically tell, it's like, okay, the slim ones here, that's single pole. These big beastly ones, they're generally the two pole breakers for 240. And they got other styles as well out there. But for residents, these are pretty much the two common factors you will have in your service panel. So now if we go ahead and look up, yeah, I know this is so much fun, right? So this rating indicates the maximum current the device can safely de-energize. And what do they mean by that? So that means like de-energized by the circuit breaker tripping or the fuse blowing or that kind of thing, basically interrupting the power feeding that given line. So if we looked at Article 110, Section 9, equipment intended to interrupt current at fault level shall have an interrupt rating not less than the nominal circuit voltage in the current that's available at the line terminals of the equipment. So if you're, and then like it says here, equipment intended to interrupt current at other than fault level shall have an interrupt rating at nominal circuit voltage not less than the current that must be interrupted. So basically meaning you can't put something in this line that's going to exceed this rating. Otherwise, basically what's going to happen is your device is going to constantly de-energize. So your line has to be designed in a certain way, and the devices that go on that line have to comply with those rules. And that's why usually, like in the lighting, they'll go with 15 amp breakers and stuff like this. You're usually very typically not, once you've got it installed and in place, your lights are going to stay the same. Okay, you're not adding in anything new or anything like that. And those are generally your 15 amp breakers that are in your service panel. And then most of your receptacles laid out throughout the house, right, to the different rooms will be on 20 amp branches. And generally in 20 amp ones are more workload and whatnot, because these are where you are going to be plugging your appliances in, your computers, your TV, your radios, your vacuum cleaner, your blow dryers, and data, you know, the 6 gazillion different things that we like to plug in our house are done on that. And usually, and you notice it's 20 amps versus the 15 amp style for the lights. And the reason being, they're more of the workhorse. They're intended to handle these heavier loads. So, and again, if you're intending for something on that line to, you know, to handle something a little more, like let's say you plan on constantly having like a space heater or something like that involved in this line, then you should have, if you designed your house for that, then you should have went through and made like a dedicated outlet for that space heater, because you don't want, because like the number 12 wiring that we usually run with the 20 amp that's feeding all your receptacles throughout the house, they're intended to handle regular things. Like I say, vacuum cleaner is probably one of the heavier duty appliances that are going to be plugged into that kind of thing. Something like a space heater now, where it's got the heating filament and it's going to be on continuously, you would probably want to size up and go to like a number 10 wiring with a little, I mean, you could probably get away with the 20 amp breaker, but you would probably want to go with a larger wire size just to avoid the heat draw that's going to happen with the current over time. But, and that's the kind of thing that we'd be talking about with the, dealing with the interrupt ratings. And if we look at our panel board, right, we're a service panel where we're putting all the breakers in and everything. You have two types. You have the fully rated and the series rated. Now, very typically, you're going to really see the fully rated one being used. Unless you go and order it as this, you generally don't see the series rated. And like I say, unless it was specifically ordered for that for whatever reason. Yes, they do tend to be less costly, but they also tend to be less safe, in the hands of an average user. So usually you go with the fully rated ones. They will be a little more costly, but they will, for the average user, it's a lot safer to use. Okay, so let's take a look at these. So here's an illustration of a typical service panel, right? There's your main breaker feed. These would be all your branch circuit feeds. You can see that our available fault current here. Okay, this would be the transformer, right? So our transformers coming in, pulling in our main power to our service circuit breaker. Service equipment must have a short circuit rating equal to or greater than the available fault current. So if we look at what's our fault current in this case, so you can see 20,800 amps, which is quite large. But again, the service equipment should be rated for that. So you would actually be able to see on there somehow that it's labeled to be able to handle an interrupt of 20,800 amps or greater. Now that's in a fully rated system. If we were to be with the series rated ones, this listing would not be available on that. But in this case, if our panel meets our requirements here, then it'll be a fully rated panel able to handle a fault current of this amount, and with no damage, minimal damage, that kind of thing, as opposed to the series rated system. Now you can see that this is laid out a little differently than this here, and that basically meaning that now we're not fused anymore, protecting it like this. Where we really are just down to what the individual devices themselves can handle, and they're the ones that are going to have their ratings on there, and that's what we're expecting to be able to deal with any problems that may occur. So all in all, I don't know, like I say, you usually don't deal with the series rated system. You can, but very typically you go with the fully rated. But you can have a lower interrupt rating, right, with the branch circuit breakers, because the combination's been tested and listed, and because it is an acceptable style system. As long as you got it in the hands of somebody that knows what they're doing on a regular basis, then you should have no trouble with that. So another topic that I look at is what's short circuit currents. Well, go with the definitions, right? A rating is required to determine the maximum available short circuit current delivered by a transformer, or kVA, right? VA being our apparent power and our capability. And notice it's in the K, so this is big stuff. And the impedance values of the transformer. So transformers used in modern electrical installations are efficient and have very low impedance values, and they do. We only really have the impedance, right, the resistance of the coils themselves, which is just copper windings. And so really your only resistance you have is the resistance of the copper wire itself, which is very, very low. So if we were looking like an Ohm's law style of application, right, and our E and our I remain the same, really as long as the R value stays in a low range like it's supposed to, then we're fine. And in the case where we deal with a short circuit, right, that's where you would have something shorting out or grounding out where it's not supposed to. What this does is it can change your resistance values, which isn't as bad as you would think with something like this, because you're already dealing with low resistance values as they have. But in any case, so short circuit current is also referred to as the fault current. So this would be like the maximum damage point that would be allowed to happen, if you will. So if we had a transformer and it's rated at 100 kVA, okay, and feeding a 120, 240 volts, it's a single phase transformer with an impedance of 1%. Find the line-to-line short circuit current. So using our basic Ohm's law here, so right, so we had, what do we have here? 100 kVA and a 120 over 240 in this case. Okay, so remember K. So the K is the 1,000. So we have 100. So 100 times 1,000 divided by the maximum voltage we're allowed to use here is 240. So if you just draw out your math, what you end up coming out with is 416 amps full load current. So if you were actually going to have this one going into your house, what you would be required to have would be 4 100 amp services. Yep, that would be 4 different 100 amp panels, or 2 200 amp services. And that would be 2 separate panels with 2 separate disconnects to them. What would be what we would be rated for in this case. So taking a look a little further at some of the math for this. And again, remember, this is really, all this is Ohm's law, very straightforward application of it, right? We're not doing anything real fancy. Now, if we look at what our transformer impedance is, in this case, you get a multiplier of 100 over the percentage of the impedance, which in this case is going to be 1. So our multiplier in this case became out to be 100. Therefore, our short circuit one is we multiply the current. Remember from previously, we got the 416. So we go 416 times the 100. And so this, what this does is it shows you that you have 41,600 amps available for line-to-line short circuit current available. So this would be your, like your maximum rating involved. And so this is what your rating that your equipment would have to have on it to be fully certified to be used for this particular service. Does that make sense? I hope. And so how do you calculate short circuit current? Surprisingly, your line to neutral short circuit current can be larger than the line to line current. And you'd have to look at how the transformer is involved and what happens when you throw neutral in there. But when you do that, yeah, believe it or not, this actually goes up quite a bit. Yeah, to the point where it's like 1.5 times larger than what your line to line. So if we were to go through that, we would say, okay, it's 41,600 by 1.5%. We would say, oh my God, so that's adding in another 20,000 into there, you know, which would make this quite a bit larger as far as what we would have to be able to, you know, be rated for. And so what that would mean is basically your equipment would have to be able to be rated for this, so that way it doesn't like blow up when this kind of short circuit current occurs. But usually when that happens, that's when it feeds back to your transformer and you hear that really loud explosion in the back. But anyway, so typical illustrations of panel boards, commercial, industrial applications. You find that they really don't change much from the way they look from a residential to a commercial to an industrial setting. Sometimes it's the sizes. like how large physically that this panel board is, like in an, let's say in an industrial setting, just because you have more things going on, more branches to feed and things like that. But as far as the size and shape and whatnot, they're pretty consistent. You could see in this case, like here, we have two different branches, right? Two hots coming in. And you notice it's very similar to this, except in this case, this one has three hots coming in, right? So in ours, we have two 120 lines coming into it with one neutral bar. So we would make two branches down this way. So circuit breakers would go here and circuit breakers would go here. So you ended up populating something a lot like this. And there's your main disconnect, and these are your branches. So these are the two hot sides here, a 120 on this side and a 120 on this side. You can tell those are your two pole breakers and your single pole breakers all fed throughout our labeling that's going through for each one. And it's very common. This is very typical of what they look like. The sizes can change, you know, depending on how large you want this to be, how many branches you think you're going to have to feed, that kind of thing. But panels, panel boards, load centers, they're pretty much all the same type of thing. They get fed a main line from somewhere, and it's going to have a main disconnect to it. And then after that, it's going to pretty much branch out, okay, and feed the various loads that, but as far as, I mean, if you're in an industrial setting and you have load centers, yeah, your main difference is you're not feeding it from the transformer off the pole, right, to your panel. It could be coming from a transformer located somewhere throughout the building, but the principle is still the same. I mean, you got one main line feed coming in, distributing out the power to different circuit breakers meant to protect those branches, and so on. So as far as like their purpose, it's the same. It's the same. It's just a matter of what it's getting fed power from and what it's feeding power to. But otherwise, it's the same principle. There's still circuit breakers involved in this and whatnot. But taking a look at it, you know, when you do buy these things, you want to make sure that the rating does meet everything that you've gone in through. So if you've gone through all your calculations and whatnot, and you say, okay, well, this is a very standard, you know, you haven't run into anything outside of the ordinary. So when you order up your panel board, you could say, okay, well, then this meets my requirements. Because I mean, when you get down, I mean, you're limited by what the weakest link is in your product, right? So whatever the overcurrent devices are, that's what it falls back. That's your extreme limitation. It's like, okay, I can't pull any more current than this is because this is my limiting factor. And everything else is sized accordingly with that. Now, non-selective coordination, that happens. It does happen. But yeah, when you have non-selective, it's like the branch breaker, the fuses might open, the main breaker, fuses might open, both might open. And it's because things are mixed matched. They're not being ideally utilized. So sometimes it all depends on the current pool and whatnot. I have seen it where the main breaker has tripped as well as the branch breakers. They both hit their time limits at the same time, and they both open up. But again, you know, it's a matter of planning. As long as you do your math in the beginning correctly, and size everything accordingly for your installation, you shouldn't run into too many problems. It's when you don't, like, you just assume and you go through and put through device or something like that, and it's underpowered, it's not quite meeting what you needed it to do, then you might run into trouble. Like if we didn't go through and do our initial calculations, let's say our house needed a 200 amp service and we ended up putting in a 150, we can't have trouble. And I mean, it just all depends. But as long as you follow through, I'm gonna stop sharing that. as long as you follow through with everything and size everything accordingly. And that's why I skipped ahead and jumped to these points, because it kind of relates to like our home installation, if you will. um, Getting panel boards selected, getting your service introduced and everything in the proper way, and what calculations are involved in doing that. As long as you go through and size everything properly, all the way down to your branch currents, and you should be fine with your workload as far as everything that's normally expected to happen in your house. And like I say, anything outside should be given some consideration, especially when you're, if you get a brand new home installation, it's the easiest, because then you're able to go everything right from the get-go. It's usually when you're dealing with things afterwards that's the problem. You got an old installation and certain breakers constantly tripping for whatever reason. You have to find out why and come up with a solution for it. So let's say you're overloaded on that given branch, but your service panel is completely populated. You have no other room. What are you going to do? Well, they do make sub panels. You can make a little mini circuit breaker panel added onto it, if you will. These are allowed. Um, where you can add in more, as long as you don't exceed the main service disconnect, you're allowed to add on to that. Generally, usually what ends up happening is you end up pulling in a new service. So if your 150 is no longer working for you, you size up and go to the 200, that type of thing. But it depends on the situation. There's always different ones. But anyway, I mean, that's pretty much what I have for everybody today. I did add, if we go here, I added some things today. Yeah, so I added an Uglies quiz and chapter 5 homework. I added those today. There's no password on the Uglies quiz. In fact, you're allowed to make a couple of attempts at it. But these answers are totally out of your Uglies book, so everything you need to have for it, you won't find in the Uglies book. I mean, you're more than welcome to look for the information elsewhere. I mean, you got Google at your fingertips, right? But let's see what I have. So I made those due. It seems this is working out the best timeline for me. So we'll make that due Thursday for chapter 5 homework and Uglies quiz number 1. And now we start tapering off a little bit. The workload won't be as bad. I had to, cram a lot into everybody's heads initially. And then Monday, well, this won't be assigned till Wednesday, but chapter 6 homework. And then hopefully by the July 1st, everybody will be able to get through all their service entrance calculations. And in fact, on Wednesday, I'll go over that. So that way, if you were struggling with it or something like that, you'll still have the whole weekend to go through and fix it up or go over areas where you're having trouble with. On Wednesday, we'll go over that service entrance worksheet, because that one's an important one. Basically, that's your initial, like, what am I designing for my house kind of thing. So I will go over that Wednesday. If you have any questions, let me know. We can get those answered for you. But that's what I have pretty much for today. That is about all that I have. Yep. Otherwise, everything else should be going along accordingly. But yeah, if you guys have any questions, if not.
No, going back to the service entrance, I actually looked around my house, and they actually put my service entrance right above my sump pump, and I have no idea how they got away with that. It's just kind of fun. That came up.
I would like a picture of that. If you could take a picture, and this is where I get my picture. But if you could take a picture of that would be awesome. It really is directly over it.
Yeah, it's kind of in this little closet off of a bedroom where my service entrance is, and yeah, the sub pump is literally almost right in the floor, basically right in front of it. No, I'll take a picture of it and I'll send it to you.
Okay. Yeah, because what could go wrong, right? Oh my God. Because I mean, all right. So I mean, just for a hypothetical. So what if your sump pump stops working correctly and it backs up? Now you get so much water involved, right? So you would literally be standing in water if you had to go to your nice electrical panel and disconnect anything. That's awesome.
Yeah, and the funny thing is, my house was only built in like 2008. It's up in Chillicothe, and I was just like, wow, I wonder how they got away with that.
You
But
do have to wonder about that if they actually had a final inspection or not. And see, and then who gets who do you get more mad at? The fact that the A, they didn't have an inspection, or B, that some bozo electrician is running around there doing this crap.
well, yeah, and then I had the house inspected before I moved in, and the house inspector didn't even say anything about it. So I didn't even know that was against code or anything when I bought the house. Now
Yeah.
I'm gonna probably deal with it somehow.
See, and that's why really in this class, the main thing to get out of this class is the code. Getting, and I mean, and there's no possible way in 8 weeks that I could possibly, feed you everything out of that damn book. But I try to get like, the more important things out of there. But yeah, it's excellent that you were able to recognize it too. Yeah, and you would be amazed at how often this happens out there. And again, it's people, and it's like, really, you're an electrician, you're a journeyman electrician, and you didn't know this, and it's like, oh my God. But yeah, yeah, huh? But yeah, I would love a picture of that. That would be awesome.
Yeah, absolutely. I'll snap one tonight and send it to you.
Okay. Yeah, that's where I get my well, I'm not really out in the job anymore, so now my pictures, they come from you guys. Where, like, can you believe somebody actually did this? It's like, yep, there it is. Look at it. Yeah.
Mine's not my main service entrance, but the I have a separate breaker when they installed my furnace and AC,
Mhm.
and it's directly over my sump pump. And a couple of years ago, I actually had a catastrophic failure with my sump pump, and I will find the picture of that and send it to you. I had absolutely no way to get in there to turn my sump pump off because it plugs in.
It's right in the way, right? Exactly. So it's like, oh.
That was a fun one. I'll be sure to find the picture and send it to you.
Okay, definitely. Yeah, because and it's like it's a giveaway. It's like, yeah, sump pumps, the bathrooms. It's like, hello, people. These are. I mean, it would be great if sump pumps never ever fail, but I've never heard of that happening yet. But yeah, the things that people will install over there. Well, that was like the last week where I showed you guys those pictures where the service panels right in the shower, and it's like, oh my God. But yep. And the scary thing is, and see, and this is why I always say, and I know some people don't agree with this or not, but whenever you get the work done, ask the guy, ask him. You ask it for a lot of people. Ask him to see his damn license. He should have a license to be doing electrical work. If he doesn't have a license, then you might want to rethink your options. It's like, yeah, maybe Joe over here is a little cheaper, but there's going to be a reason why. uh, but yeah, that's a big thing in this class. I try to get you guys, as familiar with the code as I possibly can. And this way, even later on, it's like, you know what? I'm going to go look that up. But I'll even, a little later, I'm going to share you some websites with you too, so you can be able to pull up stuff from NFPA later if you ever wanted to or need to, because you can always get their stuff off their website for free. You just can't like download the NEC book, but you can go on and look at stuff. So if anything, you always have that available to you. And if you get the textbook, you always have that available to you. But yeah. Oh yeah, they're out there. They're out there, and we're paying them. We're paying them. That's the worst part. But yeah, I'm totally against what do you call it? Half-assed working. I don't know. But that's what I say. Getting licensed is always a big thing. I mean, I'm not a big union advocate or anything like that because I think you can do perfectly fine and learn electrical without the union. But licensing, however, that's a biggie. Where if you are going to do electrical, you should have a license. I mean, even a beautician and stuff like that, they're required to have a license to operate in the state. It's like definitely an electrician. But oh god. But yeah, send me those pictures. That would be awesome. I always look for the little things where it's like, oh my god. And see, that's a good thing. If anything, you always be able to go through and recognize the things that are wrong at your house, and it's like, oh my god. Well, they had when I moved in here, they had on the same breaker. It was a 30 amp appliance breaker, but they literally have the AC motor hooked up to it and the I can't remember now, what was it? I think it was the furnace or something. But they had two separate lines going to a single breaker, and the premise being that, well, you're never going to run both of them at the same time. It's like, okay, hopefully not. But and that was from a contractor that did that. They actually the HVAC guys, when they installed it, literally installed it that way. Interesting, but anyway. But all right, yeah, send me those pictures. That would be awesome. I'd love to see it. And like I say, Wednesday we'll go over the service entrance sheet a little bit in case anybody's having trouble. Other than that, that's pretty much it for me today, guys.
Awesome. Thank you so much. You have a good day.
You too.